So far, we haven't really discussed what to do with series that potentially have negative terms. So to start with, I want to consider in particular what we call alternating series. So not only do these have negative terms, in particular, an alternating series is one whose terms alternate between positive and negative, and specifically that means every other term. So if you had a series that had a negative term followed by a negative term and then a positive term and so on, that's not alternating. It must switch signs with every term. So some examples are the following here. And one thing I really want to indicate is how you can quickly notice that you have an alternating series by the presence of -1 raised to, we'll have a couple different examples here. So in this first case, I have a -1 raised to the k minus 1. If I were to write out the terms of this sum, when k is 1, this would be positive 1 over 1. And then we would have minus 1/2 plus 1/3 minus 1/4 and so on. And so we can certainly see that the sign is alternating every other term. And this next one, if I were to write out the terms of this sum, when k is 1, this would be negative, and we'd get 1 over 1 cubed plus 1. And then, and that's negative. And then when k is 2, this becomes positive. And then negative when k is 3. And then positive when k is 4. And so on. Again, clearly alternating signs. And then in this last one, when k is 1, we get a positive 1 over 2 to the first plus 1. When k is 2, this becomes negative. When k is 3, this is positive. And when k is 4, this is negative. And this would continue. So while these all have a slightly different way of raising -1 to a power, we still obtain that alternating pattern of the sign. So in the first and the third example here, these are actually, the raising -1 to the k minus 1 is actually interchangeable with raising it to k plus 1. In both of these cases, here and here, odd index values imply that the term is positive. Whereas for this middle case, it's even index values that give us positive terms. But regardless, these are all examples of alternating series. And the key thing that you're going to kind of look for when you suspect that you have an alternating series is -1 raised to something of this sort. Okay, so to start to think about the behavior of alternating series, let's for a moment think back to all positive terms. So if I have a series with all positive terms, then the partial sums would of course be positive, but also increasing in n. So to think about that, if I had to sketch the partial sums for all positive terms, then because each successive term is positive that you're tacking on with these partial sums, we're going to have the behavior that, let's mark it off here. So when n is 1, we would get the first term of the series. When n, this should be a 1. When n is 2, we would get the sum of the first 2 terms. When n is 3, we would get the sum of the first 3 terms. And this would continue. And if the series converged, then we would expect that there would be some kind of ceiling that this would approach over time, where the vertical value there would be representative of the sum of the series. But it would always be increasing. If instead I have a situation where I have an alternating series, we can see very different behavior for the partial sums, and then that'll have consequences on how we determine whether or not the series converges. So to get just some intuition for this, I want to look at a specific alternating series. This is called the alternating harmonic series, and notice that that makes sense because the magnitude of the terms is 1 over k, but instead of them being all positive like we see in the harmonic series, these are alternating in sign, with the first term being positive, the second negative, and so on. Let's start to think about what the partial sums would look like here and how we would then plot these partial sums. So first of all, the first partial sum here would just simply be the first term, which would be 1. The second partial sum would be 1 minus a half. This simplifies to 1/2. The third partial sum would be 1 minus 1/2 plus 1/3. We could express this as 5/6. The fourth partial sum would be 1 minus 1/2 plus 1/3 minus 1/4, or 14 over 24. And in general, we could continue this, but what we can start to observe is there's really an oscillating nature involved in these plot of these partial sums. Because the first term is positive, we're going to have that actually all of the partial sums are positive because the terms are getting smaller. So even though we get oscillating behavior, this is always going to stay positive. So if I were to let the horizontal axis represent n, the number of terms we're adding together, and then in the vertical axis I want to plot the nth partial sum. What we've found so far, let's assume, so the first term we said and the first partial sum equaled 1. Let's suppose that is here, so I'm again not drawing these axes to scale. And then the next partial sum at 2 was 1/2. So that would be roughly here. And then the next partial sum was 5/6. So then we go back up, but we don't quite get all the way back up to 1. We're just short of that. And then on the next partial sum, we're going to move back down, but we don't make it all the way back down to 1/2. And so we're going to start to have this behavior. I didn't calculate the next several, but you can imagine we're going to go back up, and then we're going to go back down. And essentially, it looks as if we are oscillating around some central line here. Let's call it S, where these are going to continue to get closer and closer while hopping over it, and S would be the sum of the series. And so this is what we kind of expect to see for a converging alternating series. The plot of the partial sums is alternating. And so notice, first of all, that the growth of the partial sums should be much slower in this case than when we looked at all positive terms, where we can see every term we add on, we just get a larger partial sum. So the alternating series are actually now going to allow us to have convergence with slightly looser restrictions than when we had all positive terms. That's something we're going to see when we write down what is known as the alternating series test in a moment. But I do want to just point out now, that's because of this very different behavior. You can see that the possibility of growing can potentially be slowed down here when we have the alternating terms. So one of the things from this picture, so I will say we can draw a similar picture with the first term being negative, but we're going to have kind of slightly different behavior. So what I'll just make a note of at this point is that in that picture we have there, the first term is positive. And because of that, there are some consequences. So because the first term is positive, then that is really the reasoning for what we can observe. So let's just mark these to make these as clear as possible. This was the first partial sum, the second, the third, the fourth, the fifth, and the sixth. So notice that all of my odd indexed partial sums seem to be decreasing. as we increase n. And if this pattern were to continue, these are still always above the dotted line. But for the even index partial sums, we see the opposite behavior. S2 is smaller than S4, which is smaller than S6, and so on. And all of these are smaller than the sum of the series. So what would happen if the first term was negative is instead these would actually all sit in the fourth quadrant, and we would actually have kind of the flip of these inequalities. But we'd still have the same behavior for converging series of being able to kind of separate the odd and the even index partial sums. We're going to come back to that idea later when we talk about the notion of error and approximating an alternating series by its nth partial sum. But for now, what I want to do is simply state what the alternating series test says here. So we're considering that we have an alternating series, and one thing I want to try to make sure is clear here is this notation. So the alternating series is a sub k, where either you can represent a sub k as negative 1 to the k b times b sub k, or negative 1 to the k minus 1, this should be times b sub k, for b sub k greater than or equal to 0. All that means is I'm breaking my terms into two pieces. One, which just tells me the sign of the term. So that's the negative 1 to the k, or the negative 1 to the k minus 1. And the rest of it, the positive b sub k, that tells us the magnitude of the term. So before we move on there, let's go back to our examples. That would mean in this instance, I could split this first one into negative 1 to the k minus 1 times 1 over k. So bk here would be the 1 over k. And in this next example, bk would be k over k cubed plus 1. And here bk would be 1 over 2k plus 1. So that's all this notation means in the theorem. And just maybe one more thing, notice that in particular, if you take the absolute value of a sub k in this setup, you would get b sub k. So that's kind of the idea here. So given that, what we need to check are two conditions for the absolute value of ak, to the bk part. We want to check that the limit of b sub k as k approaches infinity is 0. And, so these both have to be true. We need the b sub k plus 1 to be smaller than b sub k, saying that the size of the terms is decreasing. If both of those hold true, that's enough for us to say that the alternating series converges. So one thing I do want to point out here, that notice that this can be a little disconcerting given the emphasis we've placed on the terms going to 0, telling us no information. It's still true that knowing that the terms go to 0 for a positive series tells us nothing about the convergence or divergence of that series. This is now only talking about an alternating sum. So, so for b sub k positive, if the limit as k approaches infinity of b sub k is 0, we don't know if the sum from 1 to infinity of b sub k converges or diverges. But if the limit of b sub k approaches, this should be a k, 0, and b sub k plus 1 is smaller than b sub k, then that's enough for us to say not that the sum of b sub k converges, but that the alternating version of that series converges. So that's a subtle distinction between when we're allowed to say something about the terms going to 0 And the other thing I want to point out here is notice that the statement of this theorem, it does not say that otherwise the series diverges. So at no point are we going to be able to say that a series diverges because of the alternating series test. What we'll have to do is look elsewhere to decide if the series converges or diverges. And I'll point out it's possible to have one of these conditions hold and one not, and either have the series converging or either have the series diverging. So that's kind of a gray area. So you want to be careful to only say that a series can converge if you use this test and these two things are true. And otherwise, we would have to move on to something else. In the next video, I'm going to go through some examples where we actually apply this test. And so we'll talk about the situation where one of these conditions may not hold and what we could do instead.